Hello, welcome to Chemistry in Action. In the past episode, we discussed solutions, which are homogeneous mixtures. Today we focus on a special type of heterogeneous mixtures, the colloids. What makes them special? We will find out after a short break. How do we distinguish colloids from solutions? As we saw in another episode, we test for the Tyndall effect or light scattering by colloidal particles. Only colloids exhibit the Tyndall effect. To scatter light effectively, particles must have dimensions approaching the wavelengths of white light. White light is a composite of 7 colors, from the shorter wavelength violet light to the longer wavelength red light. It covers a narrow region from 400 to 700 nanometers, a range well within colloidal dimensions. Particles in suspension are too large to scatter light effectively. Individual atoms and small molecules in solutions also scatter light. But the effect is not noticeable unless light passes through a thick layer of molecules like that found in the sea or atmosphere. Why is the sky blue overhead at daytime? Colloidal dust in the air plus the nitrogen and oxygen molecules scatter most of the shorter wavelength blue light and transmit most of the red. At sunset, we see a brilliant display of red to crimson colors. With the sun low in the horizon, what we observe is most of the red light that is transmitted to us. Mount Pinatubo spewed out millions of tons of volcanic dust into the air when it erupted in 1991. Since then, sunsets have been spectacular, even as far away as Australia. Without dust in the atmosphere to scatter light, the sky would appear black. Sunlight would be transmitted to us as a huge spotlight in a dark room. Dust particles in the air form a solid aerosol, a colloidal dispersion of solid in gas. In cold places like Baguio, fog is common. Motorists can hardly see through it, but because of the Tyndall effect, car headlights show up brightly. In this way, accidents are avoided. Fog, mist, and clouds are also colloidal systems. They are liquid aerosols. Even the color of our eyes can be explained by the Tyndall effect in colloids. The irises of our eyes have colloidal particles that differ in size from person to person. Other people have blue, lavender, green, hazel, or gray eyes. Variations in eye color are caused by the differing sizes of colloidal particles in the iris of their eyes. The brilliant and spectacular colors of rubies, emeralds, pearls, or images in stained glass windows are actually a selective scattering of white light by colloidal systems. In the lab, chemists use light scattering methods to determine the size of molecules of plastic and other polymers. These are materials made up of chains of large repeating molecules. Due to the fine division into particles, the colloidal state is characterized by a large surface area to volume ratio. This property makes colloids useful in cleaning up oil spills. The oily layer floating on water is dispersed or broken up into colloidal-sized particles. With a larger surface area now exposed to the sun, evaporation of the dispersed oil particles takes place more quickly. Due to their large surface area, colloidal particles have a large capacity to adsorb, that is, hold on their surfaces particles of other substances. Adsorption should not be confused with absorption. Adsorption involves penetration of other substances into a medium, as in this sponge. Adsorption takes place when colloidal dyes adhere to the surface of fabrics. Sponge nickel and palladium are used as catalysts in the manufacture of margarine. A catalyst can speed up a chemical reaction. When adsorbed on the surface of solid nickel or palladium, gaseous unsaturated oil and gaseous hydrogen combine at a faster rate. Another good adsorbent is activated carbon. We use activated carbon in gas masks to adsorb toxic or poisonous gases. Industries also use it as a decolorizing agent in the refining of vegetable oil or in the removal of organic impurities from plating baths. Alum is often added to water to purify it. The colloidal alum adsorbs the suspended particles and impurities. As the particles become too heavy, they settle out as flocks. Before our discussion gets too heavy, let's settle down with a short break. Today, we answer the question, what are colloids? Colloids are mixtures that appear homogeneous to the naked eye. They are actually made up of a dispersed phase of single large molecules or clusters of small molecules distributed evenly in a continuous phase, which may be solid, liquid, or gas. The size of colloids is usually between 1 and 1,000 nanometers. We also looked at the different properties of colloids. They exhibit the Tyndall effect. They have a large surface to volume ratio. They have a large capacity to adsorb. Adsorption is the adherence of particles of another substance onto the surface of colloidal particles. A lyophilic colloid is a stable dispersion. The dispersed phase has a strong affinity for the dispersing medium. A lyophobic colloid is less stable. The dispersed phase has very little or no affinity for the dispersing medium. What are the different forms of colloids? A sol is a colloidal dispersion of a solid in a liquid. Foam is a colloidal dispersion of a gas in a liquid. Solid foam is a colloidal dispersion of gas in a solid. An emulsion is a colloidal dispersion of a liquid in another liquid. A solid aerosol is a colloidal dispersion of solid in gas. A liquid aerosol is a colloidal dispersion of liquid in gas. In our next episode, we will continue this discussion on colloids. Until then, this is your host, Ramon Miranda, saying good day. In living systems, we encounter many stable colloids, mostly macromolecules in aqueous media. These colloids, referred to as lyophilic colloids, owe their stability to the great affinity or attraction between the dispersed phase and the dispersing medium, water. Egg white is one such colloid. The protein molecules which constitute the dispersed phase have many portions that attract water. Egg white is a sol, a colloidal dispersion of a solid in a liquid. Colloidal transformations are also possible. Watch this. If I beat this egg white continuously, the transparent colloid transforms into a frothy, opaque mass or foam. Foam is a colloidal dispersion of a gas in a liquid. If I add sugar to the beaten egg white and bake this mixture, we make meringue. Meringue is a solid foam, a colloidal dispersion of a gas in a solid. Pumice, like the species from Mount Pinatubo, is another example of solid foam. If I beat water continuously, will it also form a stable foam? No, it won't. Then, why did continuous beating of the egg white produce foam? The albumin goes into the interface between air and water and coats each air bubble to form a protective colloid. Air, in contrast, has no natural affinity for water, in which case the foam produced is a lyophobic colloid. To stabilize lyophobic colloids, a third substance is needed. Recall how we prepared mayonnaise from oil and egg yolk. The protein in egg yolk forms a protective colloid around the oil particles. This stable colloid is an emulsion, a colloidal dispersion of a liquid in another liquid. In this case, oil in water. The egg yolk protein acts as an emulsifying agent. In an earlier episode, we talked about detergent action. Let us now demonstrate this. Here are two test tubes, A and B. Test tube A, which contains oil and water, has two layers. Test tube B contains oil, water, and a little detergent. When shaken or agitated, it easily produces an emulsion. The detergent acts as an emulsifying agent. Soap or detergent molecules have two parts of opposite natures. One part is attracted to and dissolves in water. The other part is oil-loving and dissolves oily dirt. The soap molecules form micelles, which are clusters of molecules concentrated at the interface of oil and water. In micelles, the water-loving parts are in contact with water, while the oil-loving parts are oriented towards each other on the inside of the oil droplets. When clothes are washed in detergent, oil and dirt particles are trapped inside the micelles, then washed out with water during the rinsing process. Stable foams form when soapy or detergent-soaked water is flushed into our waterways. This partially blocks the sunlight needed by aquatic plants for photosynthesis. Emulsification also takes place inside our bodies. Bile is a yellow liquid produced by the liver and stored in the gallbladder. It emulsifies the food and digestive juices. Emulsification increases the area of contact between the food and digestive juices, hastening digestion. What other factors make colloids stable? If you watch television in the dark, you may observe specks of dust particles dancing in the field of light coming from the TV screen. This erratic movement of dispersed particles is characteristic of particles in lyophobic colloids. At any given time, small but many molecules of the dispersing medium collide constantly with the colloidal particles. The collisions may be unbalanced, with more solvent molecules on one side, causing the colloidal particles to move erratically. This phenomenon is called Brownian movement after Robert Brown, who first observed it in a suspension of pollen grains in water. Brownian movement provides us visual proof of the random, jerky motion of liquid and gas molecules assumed by the kinetic molecular theory. Brownian movement is believed to help stabilize lyophobic colloids by keeping the dispersed particles in suspension for an indefinite period. Meanwhile, let us suspend our discussion and take a short break. Colloids are very much a part of our everyday lives. Cow's milk, tea for breakfast, gelatin for dessert, medical and cosmetic creams, soap, shampoo and detergent, air freshener, paints, dyes and pigments, clouds, mist and dust. All these are colloids. Colloids are mixtures of substances. They appear homogeneous to the naked eye, but they are actually made up of two phases. The dispersed phase consists of single large molecules or clusters of small molecules. These particles are distributed evenly in the second phase, a continuous phase or dispersing medium which may be solid, liquid, or gas. In colloidal milk, oil globules constitute the dispersed phase. The dispersing medium is water. In 1908, Albert Einstein showed that particles ranging approximately from 1 to 1,000 nanometers exhibit the special properties of a colloid. Particles smaller than 1 nanometer form true solutions. The solute particles mingle as individual ions or molecules with the solvent molecules. Particles larger than 1,000 nanometers are insoluble and remain briefly in suspension. They soon settle due to gravity.